Section 3.4, Exponential and Logarithmic Equations. Now, there are two basic strategies for solving exponential or logarithmic equations. The first is based on the one-to-one property, and we've already gone over the one-to-one property here. So, then x must equals y. So essentially, we want those bases to be the same. So if we have the same base on both sides, we can kind of throw away those bases right here and set the exponents to each other. Pretty simple. We've gone over that in the past sections in this chapter. Also, if we have a log with the same base on each side, we can throw away those logs, right? We can get rid of them and set that x right here to equal the y here. So that is just a refresher on the one-to-one property. Now the second basic strategy for solving exponential or logarithmic equations is using the inverse property. So here we have log base a of a to the x, it equals x. So the way I look at it is, if you have these two things are the same, that a and that a, if those two things are the same in those positions, you can cancel this out and your answer is just x. Or in other words, if you have something and you raised it to that log with that same base or whatever that was, then you can kind of cancel that out too. I kind of put a cancel mark through that, and then your answer is just what's in that position. So let's try out some of these exponential and logarithmic equations and use some of the things that we've learned in the past three sections to solve these equations. The first one, example 1, 2 to the x equals 32. Now, the one-to-one property would be great here. Let me show you how. Because if we can get that 32 to also be 2 to some power, then that's the easiest method. So, for example, we have 2 to the x on the left side, but 32 also can be written as 2 to the fifth. And so we're going to use that one-to-one property here, which says if our bases are the same, then what we can do is just get rid of the bases and set those exponents equal each other. So that's how we know that x equals 5. Now you can always plug that 5 back into that exponent right there to see if the left hand side equals the right hand side. And you can see that that happens. Let me show you a whole completely different way of looking at it. But as you can see, that was pretty simple. If you understand that first method, then you're good to go with a problem of that type. But let me show you another way you could have handled that situation. You could have logged both sides, right? Let me show you what I mean about that. You could have used this version of the one-to-one property here, part B of the one-to-one properties, and you could have said log on both sides. You write the logs first. I'm going to write down the 2 here, x. As long as you have that same base though, and because what we want to happen is we want to cancel out this. So that'll be x equals log of base 2 of 32. And you could potentially change that to the log of 32 divided by log of 2. That's called a change of base formula. And you can put that in your calculator. You will get 5 also. Let me show you a whole nother way of doing this. Just to let you know that as long as you know the properties and you're using the properties correctly, you don't have to complete these equations using one method. You could put a regular log on both sides, for example. We just did log of both sides. Well, there's this power rule that says that we can x, put it in the front. Y'all remember that? X of log of 2 now equals log of 32. And then you can divide both sides by log of 2 so that we get our x by itself. We end up with what we just ended up with, which is that sort of like that change of base formula here, log of 32 over log of 2. Put that in your calculator and you should get 5. But notice that for the second and third method that I use, you needed to use a calculator versus this method. I used the one-to-one property, but I didn't have to use a calculator, right? Not necessarily if you already knew that 32 was the same thing as 2 to the 5th power. Let's move on to B. We have ln of x, that stands for natural log, because I do have, sometimes you all forget, that's not an I, that's an L for, I'm going to write it like this, natural log, all right? So the N is really natural logarithm. That's where the L is coming from, okay? Just as a reminder, it's not an IN, it's an LN. Now, the simplest thing we could do for B would be to just move this ln3 on the other side. That way it will be ln x equals, and guess what we can use? We love the one-to-one property. If we have the same log on both sides, the same base, basically we can get rid of everything else. And natural log is logarithm, but with base e. So let me write that down. ln is the same thing as log base e. So treat it as log with a base of e every time. Now, since these are the same, guess what? We can get rid of those, and we can just set x equals 3. And it's solved, right? Let me show you a whole nother way of solving that, but I think that was the simplest way to do it, because you know other properties. You know properties that involve, if it has a subtraction, right, we could use the quotient property. So I'm going to say using the quotient property, you could change it this way. You could change it as ln, right, of x divided by 3 equals 0, right, because of that subtraction. So that quotient property says if we have subtraction, we can make it a division, right? So ln x divided by 3. And what is ln again? It's really just log base e of x over 3 equals 0. So now we can change from logarithmic form to exponential form. And as you can see already, this is a longer process, right? So we can take that e right there, set it to the 0, and write equals x to the third. So e to the 0 equals x to the third. Anything to the 0 power we know equals 1 equals x over 3. And then how will we solve for x there? We could just multiply both sides by 3. Notice we're getting the same answer as before. Before though, it seemed like it was much faster. So I would stick with this one-to-one property situation. One-to-one property. It was much faster. But just showing you the range of methods that you could use to get the answers is amazing, right? As long as you know the properties, you can manipulate the problem like you want to manipulate the problem. Let's go to C. 1/3 to the x power, and then we have 9. So we already know that 3 and 9 have common factors, right? 9 has a factor of 3. But we want the base to be the same. We want the base to be 3 on both sides. At 1/3 to 3 to the negative 1, right? Because 1/3 is the same thing as 3 to the negative 1. And 9 is the same as 3 squared. Now, of course, if we have this exponent to another exponent, we can multiply that. So that's 3 to the negative x equals 3 squared. Our base are the same, so you can set, so it's sort of like you canceling out the 3's. I don't really like saying that, but it sort of is like you canceling out that, so you just set your exponents equal each other. Now we have a negative x, that's why you need to divide by -1 to get x equals -2. All right, again, that was using the one-to-one property. Let's go on to D. We have e to the x equals 7. What can we do? Well, we definitely have that x here. We kind of want that x to be not an exponent, just a regular x, right? So one thing we could do, let's do the natural log on both sides, because the natural log has a base of e. So we do natural log of both sides. We do natural log. I'm going to write it like this first, and I'm just going to drop in what D is. Natural log of e to x, natural log of 7. That way, since that ln right here is log base e, then we have another e, it'll cancel out, right? So this cancels out. We just have x now equals natural log of 7. Now, if Weber sign does not specify to approximate this solution to decimal places, you could possibly just use it, leave it as ln 7, natural log of 7, or let's get your calculators out. If it says approximated, let's put natural log of 7 in the calculator. Let's see. So the natural log of 7 is approximately 1.946, but again, if Weber sign does not say approximated or round the answer, then do not put it in there as that, because a decimal answer or a rounded decimal is not the most accurate answer. This will be the most accurate answer if the instructions do not specify to round the answer. All right, natural log of x equals -3. Let's try that. Well, one way you could do it, you could rewrite it. You know, when you see ln, it might be best to always write log base e first, so that I think that would help. Just write log base e of x. Just rewrite the problem as a log. Now, what I like doing is changing logarithmic forms to exponential forms. So let's do that. I'm going to change the logarithmic form, which is in now, is in logarithmic form. Let's change to exponential form. So what I do is I take the base and I set it and raise it to this number, and then we go back here. So that'll be e to the -3 equals x, for example. Now that is the same thing as 1 over e to the 3rd. All right, another way though, let's try using this inverse property here. This inverse property right here, B, the B part. All right, so notice it has a log, but if these bases are the same, then we can kind of cancel that log part of it, and it only leaves that x. So you can use that if you like. I prefer just changing it to exponential form, this first method here. But the second method would be just, since we know that this is a base e, we can say e to the log base e of x, or natural log of x, equals e to the -3. Again, these bases, that base here and this is the same, so that cancels. So we have x to the e to the -3. Guess what? The same as that. So whatever way you prefer, you should roll with that way. Let's try F. You have log of x equals -10. Now, what is the base if it's a common logarithm? Well, the common logarithm's base is 10, right? So this is understood as a 10 if you don't see a base log. All right, so now you could just change it to exponential form. Take that 10, take it to this power, equals that. So 10 to the -1 equals x, which is the same thing as 1/10, right? Now, if you wanted to try the inverse property, then you'll say 10 to the log of x equals 10 to the -1. Again, that cancels. Then we have x to the 10 to the -1. Guess what? Same answer. As move on to G, we have log. Now we have a base of 3 of x equals 4. Changing it to the exponential form, we'll take that 3, set it to that power, to the 4th power. So 3 to the 4th power equals x. So that's the same thing as saying x to the 81. X equals 81, or 3 to the 4th equals x equals 81. So you can just put that in your calculator, or 3 times 3 times 3 times 3 to get the 81 portion. So that's changing it to exponential form, which is my favorite way of doing it. But of course, you can always use that inverse property. We're going to use 3 this time because the base is 3 here. And that's the only way that is going to cancel, is these two things. And these two positions are the same. So again, 3 to the 4th, which is 81, we end up getting to the same step. Let's move on. Example 2, solving an exponential equation. Look at this. There are e's on both sides. So this is the one-to-one property. I love one-to-one property, especially if the bases are already the same on both sides. Then all we have to do is set the exponents to equal each other. So we're just going to set -x squared to equal -3x minus 4. Now, this is becoming a quadratic equation, right? It is a quadratic equation. I don't like my leading coefficients to be negative, so what I'm going to do is add x squared to both sides. So if we add x squared, it becomes 0 now on the left side, equals x squared. I'm already putting this in descending order. Then we know we need to factor. All right, so we need to find factors of -4 that will add to -3. And just remember, this is recorded, so you can always pause the video, work the problem out before I reveal the answer. So pause if you want to work this out before I reveal the answer. So we have x times x, that will give us that x squared. And then we know it's going to be 1 and 4 because of that -4. But since this is negative here, I want the largest number to be negative. So that's how I know it will be x plus 1 times x minus 4. But always multiply this. If you're not good at factoring, you need to always multiply your answer first before moving on to solving for x. If you're not good at factoring, repeat that. Check your multiplication, your factors by multiplying, and then once you realize it is equal to what the line was before, then you move on. Now we set each factor to 0 and we solve for x. So x equals -1 or x equals +4. We're going to move on to example 3. Solve each equation and approximate. Okay, so this one is saying approximate the result to 3 decimal places. So we're not going to leave the answer in this normal form. We actually have to round the answer. All right, so the first thing we're going to do for A is Let's divide by 3 to get rid of that 3, because we want to isolate what's in this parenthesis. We want to, or in other words, we want to get it by itself. So we divide by 3, we get 2 to the x equals, divide 42 by 3, you will get 14. So now we're in a situation like on the first page. First page, it was very nice, right? Because we know that 32 could be changed to 2 to some power. However, this one is slightly different because we cannot change 14 to 2 to some power. So that's why we, in a situation like this, we would definitely have to use other methods of solving for x using logarithmic form or exponential form. All right, so what you could do, for example, we could use this property log base a of a to the x equals x. We can use this, right? So as long as these two things are the same, then it cancels out. So that's why I'm going to write log base 2 of 2 to the x. And whatever we do on one side, which is we put log base 2, we got to put log base 2 on the right side too, or else we're not balancing our equation. We can't do something on one side of the equation and not do the same thing to the other side. Now we know that this cancels out according to this inverse property, right? Again, where did that come from? It came from this inverse property, part A. So you can use that property to get rid of things. So on the left side, we're just going to have x now because only this part counts, so not the x. So x equals, and you have log base 2 of 14, which is now you can use the change of base, right? To rewrite that as log of 14 divided by log of 2, put that in your calculator to determine what is 3 decimal places. So when I say 3 decimal places, I want 3 numbers behind the decimal. And always remember to round when you do that. So you should get approximately 3.807. Now, let me just point out, it doesn't matter if you use the log button on your calculator or the natural log button on your calculator. You should get the same answer. Let's move on to B. Let's solve for x. First, let's get rid of the 5. Subtract 5 from both sides. Then we have e to the x equals 55 now. Now, how can we get rid of this e? Well, we can use the natural log. So the natural log of e to the x equals the natural log of 55. The natural log of e cancels out. We have x. The natural log of 55, put that in your calculator. It should be approximately 4.007. All right, moving on to example 4. What should we do first? Well, it would be best to, let's add 4 first. Let's add 4. Then we have 2 times 3 to the 2t minus 5 equals 12. Now let's divide by 2. We have 3 to the 2t minus 5. I didn't write that right here, so minus 5 should be raised power equals 6. We have a 3 here. So if we want to get rid of it, we need to do log base 3 on both sides. So 3 of 2t minus 5 equals log base 3 of 6. That way, this cancels out. We're left with 2t minus 5 equals log base 3 of 6. Now we can use the change of base formula here. Change of base formula. So just remember that eventually that's what we're going to use. Let's go ahead for now, add 5 to both sides. If we add 5 to both sides, we'll get 2t equals, and you can put the 5 in front, doesn't matter, plus log base 3 of 6. Or we can treat it as and then we have this log base 3 of 6 over 2, which is the same thing as if I wrote it. This is like 1/2 times, I'm going to write it full out like this, log base 6 divided by log of 3. All right, now let's go ahead and figure out what the decimal is. So try to put all of this in your calculator correctly. You may have to just put 5 halves first and then do these two separately and add them together. I don't know what's best for you, but what you should end up with is approximately 3.315. That's how you will know you did it correctly. Moving on to example 5, we have e to the 2x minus 3 times e to the x plus 2 equals 0. Sort of looks like a trinomial, right? If you thought that, then you're right, because actually this e to the 2x is the same thing as e to the x squared. They mean the same thing. Think about it, because you multiply these two things, what do you get? 2x, right? So it's the same. Just in case. So minus 3 e to the x plus 2. So it's a trinomial. We can't factor this as e to the x times e to the x will give us that e to the 2x. What are factors of 2 that will add up to negative 3? What are factors of 2 that will add up to negative 3? So if you said negative 2 and negative 1, then you are correct, because negative 2 plus a negative 1 is negative 3. Now we set each of these factors to 0 and solve for x. All right, let's look at the first one. We can just add 2 for this. We can add 1 for this one. So now we have e to the x equals 2 here, and e to the x equals 1 here. What should we do? E to the x equals 2. So what log should we use? Log base e, or in other words, natural log of e on both sides. That'll cancel that out. X equals natural log of 2. And again, natural log of e to the x equals natural log of 1. X equals natural log of 1. Natural log of 1 is 0. What is the natural log of 2 approximately? So put that in your calculator. If you said approximately 0.693, then you let's move on to the last page. Solve logarithmic equations. I like this first one because we can use the one-to-one property. We have the same log on both sides of the equation, and it's just logs. So here's the difference between this one and this one. Notice it has a minus in this one. It has 2 logs on this side, so we can't do the one-to-one property. We can only do the one-to-one property when there's 1 log on the left side and 1 log on the right side. So just in case you were wondering, when can we use the one-to-one property? So for this one right here, there's 1 log base 3 on the left side, 1 log base 3 on the right side. Perfect for the one-to-one property. We can basically get rid of the log base 3. So now we have 5x minus 1 equals x plus 7, and then we can just solve for x. What would you do first? It doesn't matter. It doesn't matter. But I'm going to subtract x from both sides and add 1 to both sides. So if I subtract x, if 5x minus x is 4x. 7 plus 1 is 8. Divide by 4 on both sides. X equals 2. A logarithmic equations, I definitely want you to check the answers because I wonder, do you remember that you can't have a log of the negative number? So if you plug in your answer and it ends up being log of something negative, then you have to throw that answer out. So let's check this one. 5, we're going to plug in our answer, which is 2. So here's what we're looking at. Following our original equation as a guide, and we're plugging in our proposed x. We have minus 1 here equals log base 3. 2 plus 7. So does the left hand side equals the right hand side? So we have log base 3 of 10 minus 1. I guess I don't have to keep breaking it down. Y'all see that this is 10 minus 1, which is 9. And on the right side, we also have 9. So that's how we know that x equals 2 is, in fact, the correct answer. Let's move on to the right side. We have log base 6 of 3x plus 14 minus log base 6 of 5 equals log base 6 of 2x. Again, can't use the one-to-one property from the get-go because we have 2 logs on the left, on the right side. So it's not a one-to-one property just yet. But we can use some other properties. Let's think about that quotient property, because we have a minus here. Quotient property will allow us to rewrite this as log base 6, 3x plus 14 divided by 5 equals log base 6 of 2x. Now notice we have 1 log base 6 on the left side, 1 log base 6 on the right side. So therefore, we can get rid of those and just set 3x plus 14 over 5 to equals 2x. Now I want to get rid of this fraction, so I would multiply both sides by 5 to get rid of it. Then we have 3x plus 14 equals 10x. Let's subtract the 3x. We'll have 14 equals 7x, and then you can just divide by 7, x equals 2. But again, I want you to check the answer, right? So let's see, can I squeeze in a check over here? What I'm going to do is rewrite this over here. So that was 14 equals 7x divided by 7. X equals 2. Check. So the original equation was log base 6 of 3 times. We're going to plug in 2. That's what we came up with. We need to determine if this is truly the answer. Minus log base 6 of 5 equals log base 6 of 2 times 2. Right? Next up, that's log base 6 of 6 plus 14 minus log base 6 of 5 equals log base 6 of 4. Log base 6 of 20, start writing the parentheses now. 20 minus log base 6 of 5 equals log base 6 of 4. Now look at this. This right here, I could rewrite that as log base 6 of 20 divided by 5. And look at that. That's true, right? 20 divided by 5 is 4. So the left hand side is equivalent to the right hand side. All right, let's move on to the next. So because we know that x equals 2 is indeed the answer. Next, we have 5 plus 2 natural log of x equals 4. Let's subtract 5 first, because we always want to isolate that natural log or that exponential form first. So now we have 2 ln x equals -1. We can divide both sides by 2 now to get that natural log of x by itself. Natural log of x equals -1/2. Now, what is natural log of x? Natural log of x is the same as log base e, right? So what we could do, two different ways we could do it, right? Get exponential form. We want to change it to exponential form. Again, you know that natural log of x is log base e of x, right? What you could do is just take that e to that power equals that. So e to the -1/2 equals x. If we had to approximate, if the instructions say approximate it, so if the instructions read approximate this to 3 decimal places, then put that in your calculator. You should get something like 0.602. Let's say you wanted to use the inverse property. You could, right? Because the base of this is what? The base is e. So e to the natural log of x equals e to the -1/2. That will cancel that out and equals e to the -1/2. So we ended up back at that step. But always make sure that if the instructions read to approximate it to 3 decimal places, you write that decimal. Let's move on to 2 times log base 5 of 3x equals 4. Since I want to isolate my log, I will divide by 2 first. Then we'll have log base 5 of 3x equals 2. And then again, I will use exponential form, change the logarithmic form to the exponential form. So 5 squared equals 3x. 5 squared is 25. And we can divide by 3 on both sides. We get x equals 25 divided by 3. Now, what is 25 divided by 3? 8.33, something like that. But again, I want y'all to check these answers. I always check to see if this answer, you plug it into the x, does the left-hand side equal the right-hand side? Even this problem right here, let me try to squeeze in a check. But anytime you have logarithmic equations, I want you to check the answer, because it's an issue if you plug in an answer and you end up getting a log of a negative number. Then you have to throw that answer out. We have 2 times log base 5 of 3. I'll put times 25 over 3 or parentheses around that equals 4. Then the 3's cancel. We have 2 times log base 5 of 25 equals 4, which is 2 of log base 5 of 5 squared equals 4. Interesting. You can cancel that out and you have 2 times 2 equals 4, which is true because you have that 2 here and you bring down this 2 here. So the left-hand side does equal the right-hand side. So that's why you know that 25 over 3 is your answer. And if you had to approximate it, if the instructions say approximate it, the answer is 8.333. Let's go to the last problem for this lesson. Log of 5x plus log of x minus 1 equals 2. Can't use the one property right off because we have 2 logs on the left side. All right. So, but we can use the property that will allow us to multiply, right? So log of 5x times x minus 1 equals 2 because of this plus sign here. 5x times, so this really needs another parenthesis, but since we already had a parenthesis right here, then we went out to a bracket. All right. So what is our base here? Our base, this is the common logarithm. So when you don't see the base, you know that it's 10. I'm going to change this to exponential form. So 10 to the second power equals 5x times x minus 1. 10 squared is 100. If you want to, you can go ahead and multiply this. Now I can see that this 100 and this 5, these 5s have something in common. Let's go ahead and just divide both sides by 5 so that we can make this equation a little leaner, right? So we have 20 equals x squared minus x, which is a quadratic equation, we know. So that means we need to move everything to one side. Let's subtract 20. We have 0 equals x squared minus x minus 20. We can factor. When we factor, we know it's going to be x times x. We need to find factors of negative 20 that add to negative 1, right? What factors of negative 20 that will add up to negative 1? I know there's going to be 5. I know 5 and 4, but what are our signs? What sign is negative? Negative 5, positive 4. And then we're going to set each factor to 0. So negative 4 or 5. But let's check. All right. So let's check when x equals negative 4. We have log and I'm looking at the original right now, of 5 times a negative 4. So that's already a problem because see, 5 times negative 4 is negative 20. Really, we don't even have to go on. All right. I don't even have to go on for this one because look at it. We have logs of negative numbers. That's an issue because if you try to put log of negative 20 in your calculator, for example, it's going to have an error. So you can try putting log of a negative number to see what happens on your calculator. So we know already that x equals 4 is not the x equals negative 4 is not the answer. Let's try 5. Log of 5 times 5 plus log of 5 minus 1 equals 2. That's log of 25 plus log of 4 equals 2. It only has a plus, so that means I can multiply 25 times 4. That's log of 100 equals 2. And guess what? Since this is base 10, we can put this in exponential form and say, is 10 squared? All right, is 10 squared? So 10 squared equals 100? Yes. 100 equals 100. So that's how we know that x equals 5 is the only solution to this problem. This concludes our lesson on 3.4, which is solving exponential and logarithmic equations.